Hello. Um, Today we will speak about bio-inspired soft robotics for Mars exploration. Mars is the next frontier for space explorers to demonstrate the extent of human presence in space. Not only is the journey to Mars very challenging, but also it is substantial to overcome challenges for a reliable mission when the rover lands on the red planet. Thus, we will emphasize on the comprehensive planetary surface challenges. So here in this image, we can see the past, current, and future Mars rover missions, but also satellite and flybys. We can see that the past Mars rover missions include the Viking, Mars Pathfinder, Mars Polar Lander, Spirit and Opportunity, and Phoenix. The current ones include Curiosity, Insight, Perseverance, and the Chinese mission, I believe it was Turong. And of course, there will be many future missions planned. In 2021, NASA landed Perseverance, as we mentioned. So this mission its mission is to seek the signs of life and collect rocks and soil samples. And subsequently, NASA will cooperate with ESA in order to return a sample from those in Earth. Next slide, please. So robotic vehicles have been deployed for planetary exploration purposes, serving extraterrestrial terrains in research for possible life. And while deploying robotic technologies for such space mission, this represents a significant milestone for humanity. The challenges are many, as you can see. Those rovers will face they will face challenges, difficulties with power, and they will need to harness solar energy. There are severe dust storms in Mars. There are also many areas that the surface is unexplored, and thus that can be very challenging. As we mentioned before, there is a potential to send untethered soft robots, and they will be very dexterous, robust, and functional. Their rigid counterparts for planetary explorations in the future can aid in this research. Next slide, please. Okay, I give that to Rachel. Thank you.
Thanks a lot, Evangelia. So, what is soft robotics? So, any system that allows more degrees of freedom to operate along with the sensors and actuators fall under the category of soft robotics. It might make the use of pneumatics, motors, actuators, shape memory alloys to move around. And remote operations are also possible without much need to navigate the system or robot. And they're very flexible, as we can see in the image. And also they have the ability to fit into winding narrow spaces. They can be deployed, they can be easily unfolded or folded within a matter of few minutes. Next slide, please. Next slide. Yeah. So what's the need and motivation for soft robots? So as we know, humans wish to explore and settle on Mars, which needs prior studies and research. And sending humans on Mars for exploration and research is a risky affair. So it demands autonomous robots that can survive in the harsh conditions and go to the places where even we can't reach. Making use of soft robotics over traditional robotics has added advantages as it offers more flexibility, less power usage, decreased need to control the system. Next slide, please. So these are the materials that are currently being used in the domain of soft robotics, as we can see on the screen: silicon elastomers, urethanes, hydrogels, braided fabrics, hydraulic fluids and gases. And from this, you could figure out that they are pretty much elastic, unlike our traditional metal linkages, which we use in robotics. So these are the few materials, and there are some more which could be used for further space exploration. Over to you, Mangai. Thank you.
Thank you, Rachel. Yes, and a lot of the robotics that we have on Earth are we derive a lot of inspiration from what we see in the biodiversity that we have here. And similarly, we can apply that towards soft robotics. The five main concepts that can be applicable towards Mars are the cephalopod, which are all of the mollusk group for octopi, squid, and cuttlefish. Then there's a worm and slug, which have an inching forward motion, and a snake with sunflower, and arthropod, which includes all insects and segmented joints for example, spiders or scorpions or centipedes. And next slide, please. So we'll look at the cephalopod case here. What the benefits of this design are that it can be multi-limb, it can traverse difficult and off-nominal terrain. It also allows a high dexterity. If we include any tactile grips sensors, it can also climb up or down, whether it's inside a lava tube or a cave structure that's deep underground. And the soft-bodied ability allows it to adapt to whatever volume, or it can climb along the surface walls of a cave. And so out of all of these designs, I think the octopus or cephalopod design is the most advantageous, but we will also go through the other designs. Next slide, please. So NASA had created this eel robot, which is the Extant Life Surveyor. And this segmented body is excellent for traversing through long tunnels, and we assume that the lava tubes on Mars can extend to several miles. And so this would be a great exploration design. And the modular segmentation is also advantageous in climbing difficult terrain and over any obstacles. And one unique benefit is if there are sections that from end to end that are completely filled with air, we have the opportunity to send items through this air-filled chamber without being exposed to the thin atmosphere of Mars. So this is something that I think would be a great thing to look into for further research. Next slide, please. And also, we want to utilize the solar energy, and by looking into the inspiration of sunflowers, their automatic directionality towards the solar source, this would be a great way to have these soft pressure arms readjust the solar panels that are attached to the soft robot and have them directly point to the sun. And there are many more applications on Earth that we can derive inspiration from. And these are just a few of them that we think are applicable to Mars terrain exploration. Thank you. Next slide, please.
Thank you, Mangai. So I will just talk about some of the ongoing Mars rover missions and what we have learned from them. So the very first rover mission to Mars landed in 2011. During this period, we have collected a lot of scientific data. So earlier we were just making hypotheses of what could happen, but now since there are rovers there, we have collected good data. So these benefits are that we are now able to leverage on this data to build better missions. So one of the most important data we have collected is the weather patterns. So I will just pick up one robot, which is the InSight lander, which landed at Elysium Planitia at November 26, 2018. This area was a specific focus for missions, as NASA has only planned for this rover to be stuck in its same place for its entire stay in Mars. So due to its fixed location, it was able to record the temperature changes over the number of years. So what are these temperature changes? So as you can see in this graph, which is actually obtained from the NASA website, this was the temperature changes. If you look at the first, the very top box is the very top box shows the daily temperature ranges from 2019 in Earth in terms of Earth years to up till around April this year. So as you can see that, and the black line here, it shows the average of the temperature for that day. The high and the peak and the bottom of each bar for each day represents the high and the low of the day. So as you can see, the temperature is between 0 to minus 100 degrees Celsius. This mainly for location in equator in Mars, because there are other rovers being sent to other locations in Mars. But right now we just make a case study on one location in Mars. So what can we do with this data that we have? So now my colleague has mentioned about materials uses of robotics. Of course, there are some of the ongoing research and many, perhaps there have been experiments done on that robotics. We use the materials. However, most of these materials are very optimal for Earth environment's temperature. So they're used to Earth environment. You're performing research on these materials in Earth environment. So most time it works very well in Earth environment. So once you move these materials out of Earth environment, these material properties might change because of the you're now working outside of your temperature range. Most of the time, the temperature is below 0 degrees Celsius. So it might not work as well. So some of the gels sometimes are used for electricity conductivity. So when you take it out of the temperature ranges, it will not work as well. So they'll freeze and they become rigid, brittle, and non-conductive. So it's a very important finding that about temperature, because it's ruled out many soft robots which are being built with materials. So one possible solution that we uncover from our study of this area is that there's been research ongoing to build soft robot with gels that have added ionic compounds. So these gels do not freeze at temperatures far below 0 degrees Celsius, while it is able to retain its high stretchability and fracture toughness. So now that it has a very large working temperature, the material properties can remain relatively unchanged. Another important observation is the low gravity. So we know that the gravity in Mars is about almost, we are 1/3 of Earth. So what does it mean that it's less gravity? A robot will weigh less in a Mars than they do in Earth. Also, another fact is that when you're running in Earth, you're probably running, I think, quite flat on the ground. But however, if you do perform the same motion in Mars, most of the time you might possibly leap higher when you're running. So how can we leverage on this kind of like movements for robotics? So robotics movement are considered perhaps like a locomotion strategies. So currently in Mars, we have talked about wheel robots. There are many rovers which are wheeled. So now let's look at a different angle. How about leg robots with hopping? So so if you look at the image on the right, this is actually a robot called Spaceball, which was developed at the ETH Zurich in Switzerland. They had leg robots, and they're moved by one of their movement hopping. So because there's low gravity in Mars, it's easier to hop, if I'm not mistaken, than walking, than traveling through on ground. So it's easier to travel. So that would reduce the power usage of the robot. And another thing is that when you are landing in Mars, most of the time these robots are deployed autonomously from the spacecraft. So when they land on Mars, you must ensure that it's able to land slowly if it's too fast, you might land and just bounce off the surface and basically destroy the robot. So yeah, so by leveraging on this low gravity condition, we can also think of other type of locomotion strategies. How about like a tumbleweed locomotion? Tumbleweed is sometimes like you're rolling under the force of wind. So if you look at the image on the left, NASA has some advanced research on tensegrity structures which move this way. They're not being pushed by wind, but they are being controlled. I mean, with the physical, with the electric movement control on these structures on the left to navigate the terrain in Mars. So when you do this way, you're not actually you're able to travel longer, and at the same time manage to get to your destination faster, which is good. Like for right now, we are trying to get more research data to prove our many hypotheses. So this will work well in this condition. And yeah, and finally, the last slide is that as a conclusion in this presentation, we have provided a compelling case for bio-inspired soft robotics for planetary exploration, especially for Mars. As more research is done towards robotics exploration, we should take inspiration from our environment and its living organism to leverage on their amazing locomotion methods to build more efficient robots. The sooner we do so, the sooner we can move to new missions to explore other planets to gain a better understanding of our solar systems. Thank you.